we will continue. And now we will change a little bit and look at the Archaean period. So this will be something less speculative because we have rocks, so we can say something. So if we want to find some Archaean rocks, that means older than 2.5 billion years, there are many places in the world where they form some big shields. So there are, for instance, in Europe, here's Baltic Shield, Siberian Shield. There are in India, in China, Australia, South Africa, West Africa, North America, and South America with the Amazonian and the San Francisco Craton. So if we look at one of these places where we can find Archaean rocks, you recognize, I suppose, Australia. And we will look at one place located here in northwest Australia, where we have a satellite picture. The scale is given here. And we can find several kinds of rocks. First, I eliminate the rocks that are not Archaean in age. And here are granitic rocks in yellow. We have some sediments in brown and some volcanic rocks in green. And among the granitic rocks, we have old ones, the yellow ones, and late ones, younger ones, that are the red ones. And in fact, we consider that in this Archaean terrains, we have three kinds of material. We have old granite, which is generally called granite and gneiss basement. We have what we call greenstone belt, that means supracrustal rocks, that means rocks formed at the surface of the earth. It can be sediments or lava, but they emplaced at the surface of the earth. And they are called greenstone belt because the rocks are generally green. And we have the late granite. So this is the situation in Australia, but the situation is the same in all the cratons. And for instance, if we look here in South India, you have Bangalore somewhere here, Mysore here, and so on. We can see in yellow the basement, the granitic basement, in green the greenstone belts, and in red the late granite. So I can show you maps of all the Archaean cratons. We have always the same kind of material. So this is something constant in the Archaean terrains. Granite gneiss, greenstone, and late granite. If we look now at these rocks, I will show you some picture such that you could have an idea of what they are. Here is the basement. It's the basement from Greenland. They have a name, this Amitsogneisses. The age is 3.8 billion years. And you can see gray gneisses with a strong foliation. Here's the same, near Bangalore in India. These are gray gneisses, here cut by some granitic veins. And finally, the same kind of rock in the Baltic Shield. This is quite monotonous. There are always gray gneisses, not very beautiful, but these rocks are very important. And volumetrically, they are the more important rock type in Archaean terrains. Now, if we look at the greenstone beds, there is a lot of different kind of rocks. This one, which are komatiite, these are ultramafic lava with olivine crystals that make some kind of needles, as you can see here. I will explain this a little bit later. We can find also basalts here. These are pillow lava, so basalt emplaced in a lake or in the sea. So this is from Isua, 3.8 million years. And there is a lot of sediments. Here some kind of grewakis, some kind of sandstones with a typical sedimentary banding. We have conglomerate, coarse grain detrital sediments. And we have some very special rocks that are called the banded iron formation, that we call also BIF, banded iron formation. And these ones are coming from Australia, 3.4 billion years old. And something also very important in the Archaean terrain is the abundance of a rock type that is called a chert. It is mainly made of silica, and I will discuss the origin later. But you can see here in Australia a lot of these cherts, and they are very abundant in the Archaean, more abundant than today. And here is one of these cherts, it's called Marble Bar, and this is one of these cherts in Australia. What we call the late granite, which are in fact granodiorite, they are completely different from the grey gneisses. They have a lot of great crystals of feldspar in a very dark, in a black matrix, here and here too. Geologists call them sanukitoids. If you like the very strange names, you can try to remember it. Okay. So now, what can we say? And what do these rocks wanted to say to us? Here is a pillow lava, so a lava emplaced under the sea or underwater. It's coming from Barberton in South Africa, and this is komatiite. Komatiite is ultramafic rock. That means there is a lot of olivine and so on. And this kind of rocks are known only before 2.5 million years. That means that after 2.5 billion years, the Earth was not able to produce this kind of magma. So we can find pillow lava, so emplaced underwater, but we can have lava flow, just like here in Canada. And something very interesting is that in these rocks, the olivine, I think that everybody has seen a basalt with small crystals of olivine, and here the olivine crystals form needles, which is very strange, facies for this kind of rock, and this kind of texture is called spinifex. So this is something specific of this kind of rocks. And unfortunately, this is not a rock. This is only a window of a car with ice. But what we see is that if you put water, when the weather is very cold, and if you put water, ice will crystallize, giving needles like this here. And with this kind of structure, you have a main needle, and smaller needles, and even smaller here, and so on. So this structure is the structure that we observed in komatiite. We have exactly the same. And this is the reason why geologists consider that these komatiite are generated by a very rapid cooling of a very hot lava. So that was just like when you put liquid water on a car window, it will crystallize rapidly and give needle. Here we have needle because of a very rapid crystallization. One of the problems is that this kind of structure is known only in rocks older than 2.5 billion years. So here a detail of this structure. And there is some kind of empirical law that makes a relationship between the magnesium content of magmas and the temperature of the magma. So in this diagram, there is time here, magnesium content, and here the temperature deduced from magnesium content. And what we can see is something like that. That means that the komatiite and the lava emplaced during the Archaean were at temperature greater than 1,600, between 1,600 and 1,700. While today, the warmer magma are at 1,450. So obviously, the magmas, the komatiitic magma emplaced during the Archaean were warmer than the magma emplaced today. And the transition took place, well, more or less at 2.5, between 2.5 and 2.0 million years. So, first conclusion, komatiite are very high temperature magma. Now, if we look and try to compare this komatiite to the present day magma, here is a diagram with with what? Pressure here and depth, the correspondence of depth. Temperature. Here is the liquidus of the mantle. So that means that on the right, everything is liquid. This is the solidus. On the left, everything is solid. And in between, we have liquid and crystals. So that means solid and uncrystalline. If we look now at what happens today in mid-oceanic ridge, we can see that the temperature of the lava is 1,250 degrees here. If we look at what happens in hotspots, just like Hawaii or La Réunion Island, we can have temperature of about 1,400 degrees. And the melting depth is greater than for mid-ocean ridge. But when plotting in this diagram komatiite, we see that the temperature here is around 1,700 degrees, so extremely warmer. And we have here the degree of melting of the mantle. The degree of melting of the mantle is extremely high, more than 50%. So clearly, komatiite are hotter or warmer than the lava produced today, and the conclusion is something like that. The internal heat production in Earth was greater during the Archaean than that it is today. So this is a very important point. So some people made some estimation of this production of heat production. Here we have time. Here we have the Earth's heat production. So the normalizing value was the present day value for 1. And what we can say is, of course, since its accretion, the internal heat production decreases. So Earth is progressively cooling. But we can see that 4 billion years ago, the heat production in the internal Earth was four times greater than it is today. So this is something very important. There was more heat available, such that high temperature lava and high degree of melting of the mantle were possible during the Archaean, such that komatiite can be generated. And after 2.5, the Earth, after cooling, became too cold and was not able to produce high temperature magma. So it produces only basalts and this kind of rocks. So, okay, the point is that the internal heat production during the Archaean was greater than it is today. Now, we look at the second kind of rocks. The granito is a granite and a gneiss basement. So that I call also grey gneiss. And if we plot the composition of these rocks in a diagram with calcium feldspar, sodium feldspar, and potassium feldspar, we can see that most of the rocks plot in the fields of tonalite, trondhjemite, and granodiorite. You do not realize, but in this diagram there is more than 1,300 points, but all are at the same place. So that means that these rocks are very homogeneous composition, plotting in the field of tonalite, trondhjemite, and granodiorite. And as geologists are generally lazy people, they call these rocks TTG. TTG for trondhjemite, tonalite, and granodiorite. A very interesting point is that if we take these Archaean rocks, and if we want to compare them with the modern crust, when I say modern is younger than 2 giga years, we can see that the composition is different. During the Archaean, in red, the composition is TTG. And after the Archaean, the composition is from tonalite to granite. So the composition of the continental crust during the Archaean and today is different. The conclusion is that the processes of genesis, or the source of the modern and the old continental crust, were different. And we try to discuss what could be this difference. I continue with the differences. In this potassium, sodium, calcium diagram, all the Archaean rocks plot near the sodium pole. they do not follow what we call a classical calc-alkaline trend that we can see in subduction zones. When the rocks younger than 2.5 follow this trend are enriched in potassium. So if you want to put something in your memory about these rocks, Archaean rocks are sodic, modern rocks are potassic, or more potassic. As you like geochemistry, I continue. Here are rare earth patterns for Archaean rocks, for the TTG, and here are rare earth patterns for the modern continental crust. I will not comment in detail, but as the scale is exactly the same, you can see that the patterns are different. And the difference is that the Archaean rocks are strongly depleted in heavy rare earths, while the modern rocks are not depleted in heavy rare earths. So this, when we go into the intimacy of these rocks, we can also find differences between Archaean and modern continental crust. So, how can we explain this? I will not explain all the chemical modeling and so on. I will only give you the result of this modeling. The result is that these rocks were produced by two stages of melting. The first one is melting of the mantle, and the melting of this mantle produces basalts. And in a second step, this basalt, for instance, if the basalt enters in a subduction zone, this basalt at high temperature will melt and give a tonalitic magma. So there are two stages, two steps in the genesis of these rocks. And after, sometimes, it's possible to have fractional crystallization that will change a little bit the composition of the rocks. But the more important is this melting event that, in two stages, transform a rock from the mantle in a rock of the continental crust. So, okay, an important point also that we will discuss a lot of times is the presence, we need, in order to explain this, the presence of two minerals in the residue of melting. These two minerals are garnet and amphibole. About comatite, we discussed about garnet that accumulate heavy rare earths. So here it will also play a role, garnet here. So here is probably the kind of rocks that was able to melt. You can see an amphibolite, so there is amphibole in black and garnet in red. And keep this in your memory. The important point is the presence of amphibole and garnet. We need to have amphibole and garnet in the residue of melting. So, okay, this is a game. This is a result of modeling made by geochemists. We take the chemical composition, make some assumptions, some models, and we say, okay, we need this. Another possibility was to take a basalt and to melt a basalt, to really melt a basalt. So here is a press that we use in my lab, and in order to create the high pressures that we can find in the earth. And we can also heat the samples up to melting. And what we obtain, if we take a basalt and if we put it at high pressure, high temperature, we will obtain TTG magma. We will obtain magma with a static composition. And a very interesting point is that if we look now at the rare earths, here is a basalt before melting. If we melt at pressure where garnet is not stable, we will have this kind of thing, enriched in light rare earths but flat for heavy rare earths. If we have garnet in the residue of melting, we will have exactly what we have in the TTG, high light rare earth content and depletion here in heavy rare earths. So experimental petrology, experimental melting of basalt, shows that it's possible to obtain TTG by melting a basalt in the domain of stability of amphibole and garnet. So these are two approaches that converge towards the same conclusion. One is geochemical modeling, and this one is experimental petrology, and both show the same conclusion. Okay. So now, the important point we must have in mind is presence of amphibole and garnet in the residue of melting. Here is a diagram with a pressure or depth in the Earth. Here is the temperature. Here the temperature of a dry solidus, and here of hydrous solidus. So that means melting in presence of water and melting in absence of water. Here again, you see that water significantly decreases the temperature of beginning of melting. Here is a domain of stability of amphibole. Here. Here is a domain of stability of garnet. So the place here is a place where we can melt a basalt in presence of water when we have amphibole and garnet in the residue. So that means that the TTG are produced somewhere in this condition of temperature and pressure. So this is the reason why I insisted on we were obliged to have garnet and amphibole in order to explain experimental petrology and geochemical modeling, because this fixes very strong constraints. That means that somewhere the rocks was melted somewhere here in this field. So this is something important. So now, okay, we can try to look at what happens in a subduction, for example, what is happening under Chile today. So today, the oceanic crust enters in subduction under South America, and it is quite cold because it formed in the ridge. The average time is 60 million years, and during 60 million years it was at the bottom of the ocean and it cooled at very low temperature, So the geothermal gradient, as you can see here, are low, and of course they do not cut this field. But there is something worse. What is worse? I put here some dehydration reaction. So some minerals that contain water and that release water due to pressure and temperature. So this one is actinolite, chlorite, talc, zoisite, tremolite, and so on. And you see that if we follow this geothermal gradient, the subducted basalt will dehydrate before to reach the temperature of melting. And if it dehydrates before to reach its temperature of melting, that means that if there is no more water in it, its temperature of melting will not be this temperature, 700 degrees, but 1,400. So this is the reason why when you were a baby at school, you learn that it is impossible to melt a basalt in a subduction zone. Almost. So, in fact, what happens? We have here the subduction. The fluid released go through the mantle. They hydrate the mantle. And this is the mantle that melts and produces the magma from the subduction zone, the andesite, the granodiorite, and all the rocks we can find around here. So the source of magma today in a subduction zone is not the subducted slab, but the mantle. What we can propose, during the Archaean, we made TTG. So we cross the green domain here. So we can propose that this kind of gradient implies higher temperature. But this is not so stupid, because we have seen that during the Archaean we have comatite that demonstrate that the internal heat of the Earth was greater than it is today, so that the Earth was warmer. So it's not stupid to propose higher geothermal gradients. So if we follow this geothermal gradient, of course we cut the green domain, but what you see is that dehydration do not take place before, except one reaction, before reaching the temperature of melting of hydrous basalt. That means that when we reach this temperature of 600 or 700 degrees, there is still water in the basalt, and it is able to melt, because the dehydration would have taken place later. So we can assume that during the Archaean, with this kind of high geothermal gradient, this warm Earth, that was not the mantle that was melting, but the subducted basalt itself. So the source is not the mantle, but is the basalt here. And we can find the two steps of genesis of this basalt. First, from the mantle in the ridge, we generate the basalt, and second step, we melt the basalt here. Okay, we are happy with this result. as I told you, subduction, here this is the temperature in the subduction zone, consists in introducing something very cold into a warm mantle. So the slab is cold as it enters into the mantle. It is cold because it remained at the bottom of the ocean during a long period of time. So if we look at a very old crust, subducted, the geothermal gradient will be like this, because it remains 200 million years at the bottom of the ocean. If the subducted crust is younger, the geothermal gradient will be greater, and so on. And if we subduct here a very young crust, 5 or 10 million years, we can, in fact, we will subduct not a cold, but a still warm oceanic crust. So we'll introduce into the mantle not a cold oceanic crust, but a warm oceanic crust. And in this condition, it should be possible to generate TTG-like magma. So theoretically, if we can find somewhere in the world subduction of a young oceanic crust, we should predict the genesis of TTG-like magma. Of course, you know, this situation exists, and it exists in Chile, near Coyhaique, here. In fact, it exists here in the Taitao Peninsula, here in Patagonia. And what we have in fact here the South American plate, we have here the Antarctic plate, and here we have the Nazca plate. And between the Antarctic plate and the Nazca plate, we have the ridge where the oceanic crust is generated. And what you see is that here, in this point, the ridge itself is being subducted. So we subduct oceanic crust whose age is more or less 0 million years. So extremely warm. So this is a good opportunity to look at the magma in this area to see if we have some kind of TTG-like magma. In fact, in this area there are two volcanic zones. North of Coyhaique we have the South Volcanic Zone, and south of Coyhaique we have the Austral Volcanic Zone. And if we look at the age, because we know the rate of subduction and the direction of subduction, so it's possible to, we know also the angle of subduction, so to know the age of the oceanic crust below, at the bottom beneath the volcanoes. And we can see that to the south of Taitao here, we have subduction of a very young oceanic crust, younger than 20 million years, and to the north of an old oceanic crust, older than 20 million years. So, if we look at the magma generated by these volcanoes here, and these volcanoes here, we can see here that we have tonalite to granite. Here we have TTG-like. If we look at potassium, sodium, and calcium, here we have sodic magma, and to the north we have classical potassic magma. And rare earths are flat in the magma of the north and strongly fractionated to the south. These rocks produced to the south are also called adacites, but well, this is not very important. But what we see is that when we are able to produce and to subduct very young oceanic crust, we subduct a warm oceanic crust, and we can produce magma that look like the Archaean magma. So that means that the idea that we did use from geochemical modeling and from experimental petrology that say during the Archaean the Earth was warmer such that we had melting of the subducted slab and produced TTG magma is demonstrated here by the fact that where we subduct a young and hot oceanic crust, you obtain TTG magma. So this is a modern analog of what took place in the Archaean. So we can develop this idea. Here we can see the age of the crust when it enters in subduction. So when the crust is young, we have low heavy rare earth content, typical of basalt melting in subduction. And when it is old, we have high ytterbium content, typical of melting of the mantle. So what we see in Patagonia, in Chile, can be extended to the whole world. Subduction of a young crust produces TTG-like magma, and subduction of an old and cold one produces classical calcareous ones. We have seen that during the Archaean, the heat production then was greater than today. And as I told when I answered some question, the heat has necessarily been evacuated. If not, we should have general melting of the Earth. If the heat remains in the Earth, we should have melting of the whole Earth. So this doesn't exist on Earth after the magma ocean episode. The magma ocean episode was the last episode of general melting of the Earth. So, as we do not have any record of such a melting after the magma ocean, that means that this heat has been evacuated during the Archaean. And today, if we look at the thermal flux on Earth, we see that the heat is evacuated, the high geothermal gradient here, are mainly on the oceanic ridge. You can see here on all the ridge the high temperature, while in the middle of the plate or in subduction there is no this high heat flux. That means that the heat is evacuated by the ridge system. And it is evacuated by volcanism and also by hydrothermalism, but both are linked, of course. So the internal heat is evacuated at mid-oceanic ridge. So many years ago, a researcher proposed that we can correlate the amount of heat to be evacuated here. We can correlate it to the length of the ridge system. And that means that, for instance, here you have a cubic square here. That means that if you increase, for instance, the amount of heat to evacuate by 3, you need to increase the length of the ridge by cubic 27. So, okay, if we have more heat to evacuate, we can increase the length of the ridges. And, okay, so today, if you look at the plates, the typical size is several thousand of kilometers. You can see here the size of most of the plate. Why during the Archaean, if we increase the length of the ridge, we will create smaller plates. And very probably during the Archaean, there were more plates but smaller plates. So more ridge system and smaller plates. Okay, this is an assumption, but is it realistic? I propose you to discover Fiji. I've never been, so this is one of my dreams. Coconut, not with water. Okay, so the North Fiji basin is located somewhere here, and it is very interesting because we have a thermal anomaly here that is not located on the main ridges system. So we have a very important thermal anomaly, and this is one of the points of the Earth far from the main ridges where we have so high geothermal gradients. So this is one of the points where the Earth has a lot of heat to release, to evacuate. Okay, here is the North Fiji basin with the Australian plate, Pacific plate, Fiji, Vanuatu, New Caledonia here. And here is a thermal flux at in the North Fiji basin. So this is the anomaly. The thermal anomaly is located here. And so it is interesting to think how this energy is released. And in fact, if we look at this, we can see that there is a lot of ridges. These are mid-oceanic ridges. So the length of oceanic ridges here is very high. It is 20 times, by surface unit, it is 20 times more important than in the Pacific Ocean. So there is a lot of ridges, and these ridges delimitate small plates. There's a small plate here, small plate here, small one here, and a smaller one here. So what we can see here is that today, when our planet has a lot of energy to release, it will do this by increasing the length of the ridges and delimitating small plates. That means that this is not a proof, that means that this is a modern analog, and that means that the idea that during the Archaean the plates were smaller is not maybe so stupid as it could appear at the first look. So, okay. This is something interesting also, because if you increase the length of the ridges, you will also increase hydrothermalism. And if we have more ridges during the Archaean, we should have more hydrothermalism, that means more cherts. And I mentioned at the beginning that one specific aspect of the Archaean is the abundance of chert. So this abundance of chert can be correlated with the amount of ridge, the more important amount of ridge that existed during the Archaean on Earth. So this is consistent. So we have seen this picture before. If, of course, if there is more ridge, that means that there is more hydrothermalism, and maybe this could have favored some kind of chemiotrophic life. This could have some repercussion of the distribution of life on Earth at that time. Okay. So now I was speaking about comatite, about magma and so on. Now we'll try to speak about water and atmosphere. So we have seen that Jekyll Zircon says that very early on Earth, liquid water was available. One of the problems that was discussed a lot this morning was where this water is coming from. And of course, there is water in a lot of... no. Okay, there is a mistake somewhere. So there is water in a lot of material. For instance, in carbonaceous chondrite, we can have a huge amount of water in this kind of meteorite. There is also water in the micrometeorite. Here, these are micrometeorite from Antarctic. You can have between 2 and 8% of water in this micrometeorite. And of course, as said this morning, comets can provide also a lot of water. We have seen this diagram, deuterium hydrogen, here, modern oceanic water, here, with the range of composition of carbonaceous chondrite, micrometeorite, and so on, and the range for comets here. So that was the situation several years ago, and 6 years ago there was a publication about this Hartley 2 comet that has a deuterium hydrogen ratio that is more or less the same as the ocean. So it was said at the time, okay, some comets can have provided oceanic water. This is more or less true, because if we look at deuterium and hydrogen ratio, this is okay, but if we look here at DH ratio, but to nitrogen isotopes, this is not really true, because here Earth is here and Hartley 2 falls somewhere here. So this is consistent with the hydrogen isotopes, but not consistent with the nitrogen isotopes. While chondrite remain consistent for both hydrogen and nitrogen isotopes. And more recently, people from this is true, you recognize, and many people expected some important result from this comet, and this comet provided a very high ratio. So finally, one of the most common conclusions for that is that comets do not provide more than 10%, 10, 13, something, a very small amount of water to Earth. And that most of the water is coming from chondrite, some chondrites, carbonaceous chondrite, for instance, they can have during the accretion, provided Earth to the Earth. So in this case, it should have been a very early providing of water to Earth. So, okay, this is a fact. There is water during the Archaean. What kind of water? People were interested by chert. Here is a marble bar, and this is a sample of this marble bar chert. This chert is silica, SiO2, and this silica is supposed to have been precipitated from water. So that means that the isotopic composition, for instance, of this silica will be the same as the composition of the ocean. And you know that these stable isotopes, oxygen and silica, can be related to temperature. And for instance, if we try to deduce if we try to deduce the temperature of seawater from silica isotopes, here, we can find that today it's around 20 degrees, but during the Archaean, it can have been as high as 80 degrees, and between 50 and 80 degrees. So these isotopes provide some evidence of very high temperature in the Archaean seawater. If now we use oxygen isotope, we have more or less the same result. So, well, here there is a depletion that is not recorded by oxygen, but more or less very high temperature during the Archaean. This is the work done by Robert and Chaucidon. Another work done more or less at the same time gives temperature around 20 and 30 degrees. So, okay, there is disagreement depending on the approach. Some authors say, okay, we have very high temperatures, others say no. In fact, it exists two kinds of cherts. Someone has, as I said, sedimentary rocks made by precipitation from the seawater. So silica is dissolved into seawater and precipitate. So they give, it recorded the composition of the seawater. And the other type is what we call S-chert. This is a hydrothermal replacement of previous rocks. So the water percolate into a rock and precipitate, but there is reaction between the rock and the seawater. So that means that the chemical signature is not necessarily the signature of the seawater. This is some mixing between seawater signature and rock signature. Based on this, 3 years ago, Johanna Marin-Carbone proposed some criterion in order to select the good cherts, the cherts that will give that are generated by direct precipitation of silica from seawater. And using this criterion, she obtained temperature ranging between 37 and 52 degrees. So this is not 80 degrees, but that means that the oceanic, if we follow this line of evidences, that means that the temperature of the Archaean Ocean was greater than it is today. Not very much, but it was greater than it is today. In fact, one problem remains, and I have no answer for that, is that most of the cherts are formed in hydro or near hydrothermal system. So is it the temperature that we measure? Is it the temperature of the seawater in general, or is it the temperature near the hydrothermal system? So I have no answer, but this could be. As most of the cherts form in near hydrothermal system, maybe this could be affected by the temperature of the hydrothermal water. Sorry, I have no answer for that, but this is an important question. I show you in the previous talk that some minerals, just like zircon, can catch minerals crystallizing together with them in the same magma. Now, if we have a mineral, just like this one, crystallizing in water in some kind of fluid, it can also, in some default of the crystalline system, catch some water or some fluids. And in sedimentary minerals, there is a lot of this kind of fluids catched by the minerals. For instance, here, I think this is in the sedimentary quartz, and we have these defaults in the system, and there is a lot of fluid inclusions. And okay, quartz is not so beautiful, so this one is from an emerald. And there is an inclusion here. And in the inclusion, we have a lot of things. We can find salt crystal. We can have vapor, a bubble of vapor, and water with salt. So we can, in fact, some ocean water was trapped, or hydrothermal water was trapped in this mineral. So the idea is to look at this fluid inclusion in minerals in order to try to have an idea of the composition of the Archaean water. So we will look at water inclusion in Archaean minerals, hoping that they represent the composition of the seawater at the time. This study shows that, so we have looked, since the work of Daniele Pinti, we have looked at several ions and normalized to the concentration of the present day seawater. So today, the seawater has this normalized composition. And in the Archaean, there are big differences. But before to look at the differences, there are some points that are more or less identical. If we look at chlorine, bromine, sodium, potassium, magnesium, this is more or less the same concentration as today. So for these elements, the concentration of ions was more or less the same as today. But the big differences are for sulfate, iron, calcium, and strontium. So one of the first one, SO4, is today the sulfate in water is coming from the reaction of some minerals, just like here pyrite, here, that is a sulfur of iron, that react with oxygen from the atmosphere and water and give iron-free and sulfate ion in the water. And this sulfate goes to the ocean, and the sulfate that we found today in the ocean is coming from this kind of reaction. The problem is that on the early Earth, there was no oxygen, there was no dioxygen in the atmosphere. So this reaction was not possible during the Archaean because there was no oxygen in the atmosphere. So if there was no oxygen in the atmosphere, the sulfate remains in the minerals and do not go to the ocean. So this is the reason why we have a depletion of sulfate in the Archaean ocean, because there was no oxygen in the atmosphere allowing this kind of reaction. The amount of iron 2 was enormous, and we will see some consequences of that. But you know that iron 2 is soluble in water, iron 3 is not soluble, is insoluble in water. And today, of course, when iron is released by alteration of iron-bearing minerals, just like biotite in the granite or something like that, iron reacts with the oxygen in the air, and it is fixed, and it takes a red color, and we have soils made of a lot of iron from some laterite and so on. This is due to the fact that there is a reaction between the iron and oxygen. So today iron remains in place. During the Archaean, there was no oxygen in the atmosphere, so the iron liberated was iron 2, reduced form of iron. It was soluble in water and go with the river to the sea, thus accounting for the high content of iron in the Archaean seawater. Okay, we have explained two differences. The last one is a little bit more difficult to explain. This is the case for calcium and strontium. And what we know is that the CO2 content of the atmosphere decrease in course of time, from early Archaean to today, it decreased in course of time. And it's possible to, using this kind of equation, it's possible to link, to relate the CO2 content in the atmosphere to the pH of the ocean. And if we do so, we should obtain, okay, this kind of pH, saying that during the Archaean, for instance, 4 billion years ago, the pH of seawater was less than it is today. So in this condition, if the pH during the Archaean was less than today, the carbonate precipitation was less than today, resulting in higher calcium and strontium content in the oceanic water. So the high content of calcium and strontium are accounted by, or explained by, the fact that the pH of the ocean was smaller than it is today. Okay. So we have seen that the Jekyll's zircon says that continental crust existed very early on Earth. This is due to the fact that we have found granite minerals in inclusion into these zircons. Now, some people try to discuss the percentage of emerged continent on Earth. So they consider, for instance, the distribution of altitude today and the sea level is here. So we see that, of course, the continents here are generally above the sea level, but the ocean, of course, are under the sea level. And the conclusion of that is that the amount today of emerged continent is 29%. So today, the emerged continent represents 29%. So they say, and this is a very important assumption, they say today the continental crust is granitic, so its density is not very high. But they say during the Archaean, and they assert that during the Archaean, the crust was mainly basaltic, so its density was greater. And in this condition, if the density of the crust was greater, it was not so high as the continental crust today. So this assumption, this demonstration, is based on the fact that today the crust is granitic. During the Archaean, it was more basaltic. So if we take into account this possibility of a basaltic crust during the Archaean, this is what we see here. Of course, we have only 12% of emerged continent during the Archaean. So if we follow this line of thinking, it seems that the emerged continent during the Archaean were by far less than today. Today 29%, 1/3, and during the Archaean 12%. Okay, so in the Archaean less emerged continents than today. Recently, I think that was in August this year, so very recently, a group of researchers worked on the isotope of titanium in some sediments, in some shales, and these shales are coming from the destruction of the emerged continents. They are coming from destruction of continental crust and so on. And what is interesting in the approach is that they find some relationship between the isotopic composition of titanium and the silica content of the shale or of the continental crust. And of course, we have the higher delta 49 titanium with felsic crust, rich in silica, and the lower with basaltic crust here. So what is important here is to say, okay, we'll have an idea of the composition. If we look at these isotopes, we can have an idea of the composition of the continental crust that was destroyed in order to generate these sediments. And the point is this one, no very much changes. So here is ultramafic, basalt here, granite here. So if we look today, of course, yeah, we have this proportion. And if we follow the titanium isotope, we can see that during the Archaean, the amount of felsic crust was more or less the same as today. A little bit less, but more or less the same. So that means that this approach is not consistent with the assumption that during the Archaeans the crust was only basaltic. It was certainly more felsic than these authors expected. So there was no so strong changes in the composition of the continental crust in course of time, if we follow at least the isotopic evidences. So, okay, we will say that at least 12% of the continent will emerge, and probably more if we follow the result of the titanium isotopes. But we have evidence of emerged continent. We can find, so this is today, but this is during the Archaean, mud cracks. This is what we found in ponds after evaporation of water. The sediments, the mud cracks, so we can have this kind of thing. We can find, so this is in rocks at 3.4 billion years. We have some evaporite with gypsum and barite crystals here in these rocks. So evaporite is a result of evaporation of water, just like salt in seawater. So this indicates that some parts of the continent were emerged. Of course, if you say continental crust, we do not say automatically emerge, and we know some emerged places on Earth that are not continental crust. If you take Iceland, Hawaii, of course they are emerged lands, but they are not continental crust. So, okay, so the problem is not so simple. Why discuss this point? This is because if we look at the repartition of nutriments in the ocean today, the red is a lot of nutriments, less is in blue and violet. We can see that most of the nutriments are located at the vicinity of continents, here, and in cold water, but here, just on the limit of the continents, and most of these nutriments are carried from the continent to the seawater. So the fact that we have emerged continent has some link with the amount of nutriments in the water. And of course, the amount of nutriments is linked to life, for at least its development. I don't know for its appearance, but for the development of life, this is something that can be important. Okay. South Africa, in terrains at 3.2 billion years, there are sandstones that you can see here with a very strange stratification here, like this, like this, like that. And this kind of stratification that we can see here, flat here, like this, etc. This kind of stratification has been interpreted as resulting of some current, of some displacement of water. And the people who study this related this to the effect of tide. So that means that when water is going up, it will deposit some sands. When it go back, it will remove one part, and when we come up again, deposit new sand, and so on. So they say this kind of cycle is linked to tide, and this is well known in other places of the world. This is more recent sediment. This is modern tidal sediments, but we can see some rhythm here, which is the rhythm of tides, which is something important. So, in Barberton, they study these tides, and they show that there is some rhythmicity in these tides, but that the rhythmicity was not the same as today. It was anomalistic months was of 20 days. Today it is 28 something or 27 or something, I don't know. And that the length of the day was only of 11 hours. And this is due to the fact that the moon was closer to the Earth. The same studies were performed on more recent, for instance, some shells and so on. And it was possible to build this kind of diagram. So you have the length of a day in hours, the time. So today is 24 hours. And several kind of rocks were studied. Some sandstone, some stromatolite, some animals, some shells of animals. And of course, it was possible to draw a line. It would have been possible also to draw this one. But obviously, it is clear that the length of the day was shorter during the Archaean than it is today. And this is due to the fact that the moon was closer to the Earth. And the fact that the moon was closer to the Earth has effects, because the tides were more important than they are today. And some people calculate, maybe 12 years ago, that on a flat land, the sea, due to tides, can penetrate into the land on distance about 100 kilometers. So this means that this could be important, because this water, even if this is not 100 kilometers, this water will erode the continent and take a lot of nutrients to carry to the ocean. So the effect of these tides would have been very important. And some people, for instance, say, this is a model by Comeras et al. They say that in order to realize peptide synthesis, one possibility is alternation of dry period and aqueous period. So this kind of important tides can provide dry period and aqueous period. So this could have influence of life. Also, other people propose fast tidal cycling and the origin of life. So they say that the origin of life can be related to these important tides during the Archaean. And so, okay, they developed the idea. And one of the ideas is that this tide will have create some fluid flow, some water flow, that can have effect on the, for instance, of the sheet of mica and so on, and help in developing some molecule in between the sheet of mica. So the sheet of mica will, when there is a lot of flux of water, they will open. When the water removes the clothes, and this motion could help in the production of not life, but maybe some prebiotic chemistry. So I am not at all biologist, so I don't know if this is realistic or not. But what I would say as geologist is that tides were very important and could have had importance on life. But I cannot explain this, and I don't know if this is realistic or not. But I would like to follow this kind of thing. Okay. Now, another point that I would like to address is the activity of the sun. So here is time, and here is the luminosity of the sun divided by the present day luminosity. And so what you know is that 4 billion years ago, the sun was, let us say, colder than it is today. Its luminosity was about 30% less than it is today. So, okay, in other words, our planet receives less energy from the sun than it receives today. Here is the temperature at the surface of the planet. If we take Earth and we remove the whole atmosphere, the temperature would remain extremely low even today. Now, if we consider the atmosphere with the present day atmosphere, we can see that the temperature will be above 0, as it is today. But the prediction is that up to 2.2 million years, the temperature would have been lower than 0 degree. So maybe this could have resulted in a frozen Earth. So theoretically, what we can say is that as the luminosity of the sun, as the energy that the Earth received from the sun was less than today, we should have had a frozen Earth before 2.2 billion years. The problem is that we have no evidence at all for that. We have no diamictite, just like this one, which is produced by glacial activity. We have another diamictite here. We have no striated pebbles that we have in glaciers today. So there is no evidence for general cooling and freezing of the Earth before 2.2. So the only possibility is that the composition of the atmosphere was not the same as it is today. We have a more efficient greenhouse gas in the atmosphere in order to maintain temperature above 0 degree, even if the energy received from the sun was less than it is today. Okay. I don't know why I have done this. Okay. So this is again a work by Daniele Pinti that tried to explain what was the evolution of the atmosphere and of the ocean. If we consider that the whole carbonate that we have today on Earth were in fact under the form of CO2 in the atmosphere, the prediction are pressure between 40 and 210 bars of CO2 in the atmosphere, pressure in the atmosphere, so which is very high. And there was also at that time water was in the atmosphere, so there was also high pressure, partial pressure of water. Water fall down on the Earth very early, as we have seen, because we have seen that liquid water was available on the surface very early. And part of the CO2 that remained in the atmosphere was recycled, maybe due to subduction, into the mantle, but also in the ocean. And probably you know this kind of thing better than me. Of course, CO2 can be released by volcanoes. Rain carries some water and carbonic acid to a continent. So they react with the continental crust, go to the ocean, and precipitate to form carbonate sediments. And these carbonate sediments, so this is some kind of extraction of CO2 from the atmosphere to the rocks, and part of this can be recycled to the mantle through subduction. Okay, so here, for instance, is CO2 that is fixed by animals and form carbonates in these cliffs in France. So what I would like to say is that there are some mechanisms of extraction of CO2 from the atmosphere to the rocks or to the mantle. So probably that the composition of the atmosphere evolved by decrease of CO2 content in this atmosphere, very high CO2 content in the early Earth, and decrease in course of time. Okay. Now there is also a gas that is important in the atmosphere, is oxygen. For us, at least, it is important. And we can have explanation looking at this banded iron formation that we have, for instance, here in Australia, and that are very abundant in the Archaean and early Proterozoic. So here are some pictures of this iron formation with the alternation of iron and silica layers. I like this picture, so I put this one. And you remember that we have seen that iron 2 is mobile and iron 3 is not mobile in water. So if there is no oxygen in the atmosphere, the iron produced by alteration of the rock will dissolve into rivers and will go to the ocean. And we have seen that the iron 2 content of the ocean was very high during the Archaean compared with today. So today the situation is different because there is oxygen in the atmosphere, so the iron is oxidized and it remains at the surface just forming some kind of laterite. Just this is what we can see here. The iron is iron-free and fixed on the land, and it doesn't migrate to the ocean. Okay. So the situation for the Archaean was, of course, the atmosphere, there was no oxygen, so it was reducing. The ocean was also reducing. So the content of the ocean of iron 2 was very high. But when we look at this banded iron formation, you notice that the iron is red and this is iron 3. So necessarily there was precipitation of iron 3. So the hypothesis that seems to be realistic is that it existed some oxidizing oasis, for instance some cyanobacteria in stromatolite or something like that, that locally produce small amounts of oxygen such that the iron that was dissolved in the water changed from iron 2 to iron 3 and precipitated, thus giving the banded iron formation. In course of time, of course, the development of life increases such that the upper part of the ocean become oxidizing and making the precipitation, resulting in the precipitation of most of the iron dissolved in the water. So this is the period where we found big banded iron formation, huge amount of iron due to this oxidation of the upper part of the atmosphere. And after this period up to 0.6 was oxidizing atmosphere, oxidizing upper ocean, reducing bottom of the ocean. And today, everything is oxidizing, except some reducing oases near the black and white smokers. So we started with a world with atmosphere and ocean reducing, and some small oxidizing oases. And we finished today with everything oxidizing, except some reducing oases. So the question is to know when the atmosphere became oxidizing. So the banded iron formation can give an information about this, because when we find a lot of banded iron formation, which is the case here, we can say, okay, that was the beginning of oxidation, at least of the upper part of the ocean, and probably beginning of the atmosphere, in the atmosphere. The limit is 2.2 billion years. There is another system that is interesting to look at, is the system of uraninite. It works in a different way. The oxidized form of uranium is soluble, and the reduced is not soluble. And we can find a lot of deposit before 2.2 and almost nothing after 2.2 billion years. I just would like to say a few words about something strange. It is a natural atomic reactor from Oklo in Gabon. It is located somewhere here. And okay, here is the place. This is an old quarry. And this is a natural atomic reactor. Another picture of this. And the geology is very simple. There is TTG, so Archaean basement, sandstone, and black shales here. And the age is 195 gigayears. So the people who discovered this were analyzing isotopes of uranium, and they find that there was some the uranium contained in this layer was impoverished in 235 uranium. Even if the difference is not big, it is very significant. So the conclusion was there had a natural atomic reactor in this area. So in order to operate, this atomic reactor requires uranium sufficiently rich in 235 isotope. So at the time of this reactor, the ratio was 3.68, so that was sufficiently high because the limit is 3%. It was just above the value. We need to have a sufficient critical mass. We need to have concentration of uranium. And also, we need to have some element in order to moderate the reaction. And these elements can be water, but organic matter also. And we have seen that above these reactors, there were some black shells, and these black shells are this black shell consists on sediment with carbon. So, okay, here is the situation: Archaean basement, sandstone, black shell, and water penetrate in these rocks. Uranium was dissolved by water and accumulate in this place here along the faults in the contact between the black shell and the sandstone. So we need to have transport and concentration of uranium. So if we look at the ratio 35-38 uranium isotopes in course of time, the first condition, okay, here's the decay. The first condition is that in order to the reaction to start is to have a ratio greater than 3. So we can eliminate this part of the diagram where the value of the ratio is lower than 3. We also need to have a period where it was possible to concentrate uranium. And in order to concentrate uranium, we need to have oxygen in the atmosphere. And we have seen that oxygen appeared more or less at 2.2 billion years. Because we need, in order to be mobile, uranium need to be in an oxidizing environment. So we can eliminate all this part. And we can see that in order to have this reaction, we have only a very small window when it was possible to have this reaction. This is the age is okay, 195, and the ratio was this ratio here, 3.68. But what is interesting in this case is that there was a very small window for this reactor to take place, and of course it can take place only when it was possible to concentrate uranium. That means only after the apparition of dioxygen in the atmosphere. So the limit is also before this one. Last point for atmosphere. If we look at sulfur and the isotope of sulfur here, we can say that the sulfur isotope, the fractionation of these isotopes depends on their mass. In this condition, if there is no UV, the fractionation depends on the mass, and it will follow a law, that is this law, that is represented by this line here. And if the fractionation is dependent on the mass, we will have points falling on the line here. This is the general case today. But if now we imagine a situation where we have UV ray reaching the surface of the Earth, in this case, the fractionation will not be mass dependent. And we will have a very big possibilities of values for this isotope sulfur fractionation. Okay, this is two kinds. If we have not UV, this means mass dependent. If we have UV, this will not be mass dependent. So if we look now at the distribution of sulfur isotope in the Earth's history, we see that after 2.2, so in the Archaean, the distribution was not mass dependent. That means that the UV can reach the surface of the Earth. And after 2.2, up today, the fractionation was mass dependent. That means that UV were not able to reach the surface of the Earth, and we know that UV today are stopped by the ozone layer. That means that by the presence of oxygen, because ozone layer formed by reaction with dioxygen. So this diagram is very important because it indicates that the oxygenation of the atmosphere appeared more or less at 2.2 billion years. So this, the atomic reactor, the bonded iron formation, everything is going in the same direction for apparition of dioxygen in the atmosphere at more or less 2.2 billion years. Okay. We will see in the last part in 2 minutes that in fact oxygen appeared in the atmosphere at 2.2, but that in fact living beings were able to produce oxygen since at least 3.4 or something like that. So there was a delay in the oxygenation of the atmosphere. And many assumptions were proposed. I don't know what is a good one, if it is among this one. Some people propose that in order to have oxygenation, we need to have organic carbon efficiently sequestered after the death of the organism, because if not, carbon will react with oxygen and in order to produce CO2. Others propose that the oxygen dissolved in the ocean has to be oxidized before the oxygen moves to the atmosphere. Other authors propose that oxygen was used to oxidize the mantle. So this, I think that this assumption we can eliminate, because when we look at the degree of oxidation of Archaean basalt and modern basalt, the degree of oxidation is the same. So there is no evidence of reduced basalt composition in the Archaean. And others propose some kind of competition between cyanobacteria and metallurgen. I don't know what is a good one, but there is a lot of people that propose hypotheses in order to explain the delay in atmosphere oxygenation. Okay. The last point is, what about early life? The first point is that we have two evolutions of the sources of energy. The internal energy is decreasing in course of time since the beginning of the Earth, and it becomes less and less favorable to chemotrophic form of life, from life related, for instance, to black smoker and so on. While the temperature or the energy provided by the sun increases in course of time, and this is more and more favorable for phototrophic forms of life. So there was a decreasing of one source of energy, increasing of the other one, and this would favor different kinds of life. And now I just would like to say a few words about the traces of life that we can find on Earth. So there are undisputed evidences. This is, for instance, the stromatolite from Pilbara, from the Tumbiana in Australia. I suppose that everybody knows stromatolites. This is, for instance, these ones are in a lake. This one are in Shark Bay, in the sea. And This is accumulation of minerals, of grain of sands, or linked to the presence of biological films, or presence of life in this environment. So, for instance, this one in Tubiana is not disputed because there were found some traces of bacteria in this stromatolite encrusted by iron oxide. So there is a direct link between the bacteria and the stromatolite. So, okay, this is obviously an evidence for life. In North Pole, in Australia, there are some traces of stromatolite, but I say nearly attested evidence. Most of the people believe that this is trace for life, but some say, okay, this can be some deformation of the rocks and so on. For instance, here you see, okay, so you see this stromatolite. The problem, my photo is not a good one, but you have this stromatolite like this, and the bottom is flat. So that means that this is not a fault, because the fault would have affected all the levels. So, okay, I think that most of the geologists now believe that these are stromatolites. More recently, that was last or 2 years ago, Nutman and collaborators in Australia work in Isua sediments in Greenland, so in this environment, and they found this kind of structure that was in last year. And they found this kind of structure here in the sediments. So you have the scale, this is very small structure, and they interpret this in terms of stromatolite. They say these are stromatolite, and maybe you have seen, I don't remember if this was in Nature or in Science, the oldest forms of life and so on and so on. Okay, there is in the literature after a lot of comments because this is very small scale. So now they try, the group of Australia, try to find more evidence for carbon, the presence of carbon in these sediments and so on. So, okay, this is, people call this stromatolite, but this is quite a lot discussed. And the last one are evidence provided by in different places. These ones are in Greenland. And in these rocks, it's possible to find, for instance, here, apatite crystal. Apatite is a phosphate. And that contains graphite. And here there is graphite. These rocks are 3.86 billion years. So they contain graphite. Maybe you have seen this that has been published this year. In Nuvvuagittuq, 3.7 billion years. There are some tubes, or interpreted in terms of tubes. So this is the sample, this is the interpretation. And in this tube, there is some graphite here. And finally, the last point is in the zircons from Jack Hills, so very old ones. There is also graphite. There are some pieces of graphite. So, okay, this graphite has been analyzed from, of course, graphite is carbon. So, for carbon isotopes. And, okay, this value here represents the ratio, more or less the ratio between 13 carbon and 12 carbon. Okay, so this approach is very interesting because here is a range of composition for inorganic elements, just like ocean water, atmosphere. Most of the rocks fall in this range of value. Here is organic carbon, so in bacteria and in living beings. So it seems that there is a range here where there is no overlap of the values, and between -20 and -50, it seems that this is typically isotopic signature linked to organic, to life. And when we plot in this diagram the graphite from Isua or Aquilia, the graphite from Nuvvuagittuq here in the tube, and the graphite in Jack Hills, okay, they plot in the domain reserved for biologic carbon. And the authors of this paper say, okay, we have found isotopic carbon signature typical of life. Of course, there is a but. And the but is when these rocks are metamorphosed, that means when they are heated, when they go deep into the earth and when pressure and temperature increase, of course, this increase of temperature and pressure modify the isotopic signature. And here you have the range of isotopic signature of these metamorphic rocks. So that means that this signature could be life, but could be also metamorphic. So this is not a proof that this carbon is linked to life. It could be linked to metamorphism. And for instance, for me it's quite difficult to imagine, for instance, if you take Jekyll zircon. The zircons crystallize in a granite. For me it's difficult to see how graphite linked to life could be in a granite. So, okay. So you can interpret this as you want, but there is a very strong doubt here due to the fact that metamorphism can re-modify the isotopic signature. So this looks like biological, but can be purely abiotic signature.